Yeah, welcome back. Hello, everybody, and welcome to the example 2 in SuperPro Designer for Bioengineers. Yeah, welcome back. Now we're starting with example 2. Now the first example, example 1, was about a very, very simple neutralization process. Neutralization process, of course, it's nice, but it's not of real relevance. But now we want to set up a real fermentation process. And the second point is usually a process doesn't consist of one unit. You have several units. So that's what we do now. And then we take at the end, we will also take care about debottlenecking and so on. So we come closer to the reality. Of course, the basic steps which have been described in example 1 will not be described again here in depth. So this you use then your example 1 sheet as a reference for this case. And this is how we proceed. So as you see here, the purpose is setting up a simple fermentation process for the production of yeast. So we want to produce biomass, including basic upstream and downstream procedures. And the production target is 30 kilograms yeast per batch. The maximum reachable cell density is 20 grams per liter. You remember in your exam you have calculated that. This is the link to bioprocess engineering. We inoculate with 1 gram per liter. And we don't care at that point about sterility, which is, of course, certainly a good idea if we set up a bioprocess. Now, the intention here is setting up the fermentation process, one thing, of course, but also scheduling is the intention of up and downstream processes and the debottlenecking and process optimization. Now, the first part was a part where you should do the calculation. So also with a software like SuperPro Designer, your background in bioprocess engineering is warmly welcome. And this part should show you that still you need to feed the software with something. And this needs to come from somewhere. In this case, it comes from your knowledge in bioprocess engineering. So we will just use the result, but I warmly invite you redo these calculations on your own. It's important that you understand what is happening there. And now we will go and just start with setting up the process. So setting up the process. So we want to start a new fermentation procedure. So of course, if we want to use a fermentation procedure, what we need is a bioreactor. So we need to put in a bioreactor in our process. And before we do that, of course, we need to register our substances. The first step is always registering pure components. I have already started now a new batch process as last time. And now I start with registering the substances. So here we go. So we go to as it's the same as you did last time, so not much to say. Pure components, I don't register mixtures, I register the substances itself. So what we have is we have glucose and carbon dioxide. So this was the easy part because these are in the list. And we have distiller soluble. So distiller soluble is, of course, not a substance. Distiller soluble is, of course, a mixture. So the question is how to register a mixture. This is composed of several components, and we have talked of in industrial biotechnology a couple of minutes ago that this is complex. I don't even know the composition there exactly. And the cool thing is now we don't care about the exact composition. We just need to know this is an organic soluble compound, full stop, distiller soluble. So at that point, we just handle distiller soluble as being similar to glucose. It's for us, it's a substance. Yeah, and you could do if you split that up later on and so on. We can talk about that. But at that point, we just think distiller soluble is a substance which goes into the reaction with glucose and oxygen and gives us yeast. Full stop. That's fine. No problem. So let's go. So we go to the register edit pure components dialog. And what we do now is as we have it not in the database, of course, if you look for distiller soluble, nothing will be in. So what we do is we register add a new component. So this is this part here, add a new component. So we click on this. Then we get this dialog, new component definition. So the name is, we just put in the name, distillers soluble. Okay, so this is our new component. And now we can use a reference for default property values. So now we say, what is the reference here? But what we say, it's an organic solve compound. And at the end, it's these things look different, similar from the composition, like a carbohydrate. So why not using just glucose as a reference compound? If we need more precise things later on, then we can work on that. But with glucose, we have already a COD and so on. So we have many values which are fair with respect. It's better than using a salt. It's fair. It's an organic compound, full stop. Then let's start with glucose. Then you don't need to initialize all parameters from the scratch. So now we have already something and we say, okay, we're happy. But of course, we keep in mind that this is not the exact composition which is inside of that. And another component which we need to now register is yeast. Yeast is even way far away from a substance. It's biomass. So the cool thing is it's already in the pure components data bank, in contrast to what is set on this in the script. So you see that here we have our yeast. So therefore, if it's there, we take it. Otherwise, we could do exactly the same as we did for distiller soluble, just make a new compound. And also here, I would recommend use as a reference yeast in this case, glucose in this case. But we have it. And now we register. And now yeast is somehow special. Oh, it misses the vapor pressure. This makes us not too nervous for yeast. Okay. But yeast is our biomass. And we need to tell the software that yeast is our biomass. If we double click, for example, for distiller soluble, you see here that we have filled everything out. And you see that this has copied now the values here from glucose, the chemical oxygen demand, for example, or even the biological oxygen demand. But here is a small thing to click if it's biomass, because for some processes, biomass is treated differently. And yeast, of course, is biomass. And you see it's already clicked here. So yeast is biomass. If we would have started that from by new, then we would have to click it. And you see the formula of yeast here is the formula of glucose. So the yeast which was inside there is treated as being glucose. So they have also initialized it with glucose. Okay, it's biomass. And then we need to tell the software that the primary, this is down here, the primary biomass composition, first of all, what is our biomass? It's yeast, again. And it's composed of 80% water, and the remaining part is then the dry mass. Of course, you can change that also. If you know the composition of your microorganism, you can also refine that. But in general, this is not necessary. So it's engineering. Just do the things which are necessary. So we have now defined our substances. And as you see, we have defined now a substance which is completely new, which is now present. It's just an organic substance. And for this, we need use as a reference glucose. We have defined yeast as our biomass. We have used it from the database, but we could have done the same as we have done with distiller soluble. Just we need to click this is biomass stuff. So that's all we need. I don't do, in this case, I don't bother with respect to mixtures and so on. This was the question before. And now we go to 2.2.1.2 and we add a fermenter and streams, and we initialize the streams. Well, how do we do that? Of course, we now go to unit procedures, go for a batch vessel procedure. And now instead of using a procedure in a reactor, we want to do a fermenter. And here we added So this is our bioreactor, and this is what we have added now. And now we need to draw the streams, and we do the same as it's depicted here in this picture. So we need a stream for glucose. So for assigning streams, of course, you remember we have to click on the connect mode, and then stream 1 here. And we have distiller soluble here, and we have water stream, and we have one stream for the air. So we have 4 streams going in. We have a vent stream going out, and as you see, as soon as we go close to this ports, the arrow changes. Click, click, double click, and click, click, double click. So what you should do right now is assign the streams that you can read it, so label it. So the first one is glucose, so we just right click, edit labels, glucose. The next one is, it was distiller soluble. Okay, so of course in the stream nothing has changed. We have just at the first beginning, when we have drawn it, we have already assigned the name to make it easier and later on to attribute everything. So remember at the neutralization vessels, we just had 4 streams. It's 101 until 104. So you could work with that, but you need to be able to have an overview of what is happening. So what you should do is directly after drawing the streams, I recommend you already initialize them. So tell the software what is in the stream. So glucose, of course, we have glucose inside. Distiller soluble, I just double click on the stream and I bring distiller soluble inside of the stream. Just label distiller soluble now also has distiller soluble inside. The same is true for the stream labeled with water. We bring water inside. And for the stream labeled with air, we bring the stock mixture air inside. This is already pre-registered, you remember this stock mixture. So now we have initialized the streams in a way that all stream compositions are associated with these charged streams. So now we go to the point 213 and we add operations. So it's the same as we have done last time. We right click on the bioreactor and choose add remove operations. Now, what operations do we have to add here? Now, obviously, we have, with the exception of air, we have to charge 3 things. So we will need 3 charge operations. 1, 2, 3. Then we add a heat operation. I come to it in a second for what we do that. We add a ferment operation. Sorry, ferment operation. Not react, ferment. It's a bioreactor. But also here, if we make life easy, we use a stoichiometric fermentation. And we then at the end have a transfer out operation. So we have, looks very similar to what we have done in the neutralization. We have charge, here we heat. So we realize that if we bring in the water, it comes in with 15 degrees. It makes no sense to start directly with the reaction. So we need to heat it up. And this takes time. You remember, this is a reactor then with 1,500 kilogram water. You need some heating and this costs energy. This is not done in 1 minute. And then, of course, we do the fermentation itself, and we have the transfer out. Now we have a point that we say, we need to inoculate, yeah, and we have not. There was no stream with yeast getting in without inoculation. Here, there will be no. There will be nothing. Nothing will happen. So what we do here is what we use is a trick. We just put a hold operation. A hold operation is our operation which simply makes nothing. And insert this hold operation just between the heat and the ferment operation. And this operation, which is just do nothing, we rename and name it as inoculation. Okay. So at the end, of course, there is no operation happening there. We just take this as, remember we need to inoculate, and this takes half an hour. But we neglect that we bring this biomass in, because at the end it's neglectable compared to what is being produced. This makes the process easier. So of course you could, but it's not forbidden to make a real inoculation. And if you have a seed train, you will have that. But the first inoculation, the start inoculation, usually is done like that. And of course, this means that the simulation produces then biomass from nowhere, which doesn't work, but we don't care. So we just want to have this this whole operation there in order that we take care about the time which takes this operation. Okay, now we have all our operations and we go okay. So up to now, again, nothing new. This is the same as we have done with the neutralization process, just we have used nothing new. We have used another operation. It's a fermentation. It's no more a reaction. And second, what we also have introduced is we have this heat to heat everything up. So now we need to initialize the operation. So we have now just added, we have initialized the streams, we have added the operations, but now of course we need to initialize them. So let's go operation data, and we go to the charge one operation. Here we are. So the first operation, we want to charge glucose. Now all our streams have been initialized already with a concentration, so we don't need to care about that. This is, as I said, this is the way I do it usually. I just put the content for charge streams in the stream, and then I just need to use the amount. Now, how much do we have to load? If you would have done the calculation, you know that we do that in 1,500 liters equal kilograms, and then we can to produce the yeast amount of yeast we want, we need 50 kilograms glucose. It's a very wise idea to redo this calculation. Now, the process time, it is set in our description here. For solids, it should be set to 1 hour. So we do set by user. You could here to see that it calculates mass flow rates or volumetric flow rates. So it calculates that for 50 kilograms, we would needs a couple of minutes. However, if it's, for example, a GMP process and so on, this takes longer. So we say it takes 1 hour to charge that. If you don't know, if you have not any idea, keep these default values here because they're usually quite reasonable. So we know that to go to the next step, we can use this one. And this is now the second what we charge. It's distiller soluble. And there, if you would have done the calculation, we know that we need to charge 1 kilogram of distiller soluble. It's 1% of the yeast, as you have seen in the equation. However, we should make not the yeast of the glucose, but we want to make the glucose limiting and not the distiller soluble. So we use the double amount of distiller soluble. Therefore, we charge 1 kilogram. And also here we say that it takes an hour. And just, it's not a minute. Yeah, it was a minute, so it was not an hour here. So this just went back. So now it's an hour. Okay, next is our water. And this is then calculated, it's liquid, and then we can use this mass flow rate, or we should set the volumetric flow rate of 600 liters per hour. Okay, then the next is the heat operation. Now let's check what he says to the heat operation, and we want to heat up not to 50 degrees, we want to heat up to 30 degrees. All other parameters we are asked to leave unchanged. And what we could do now is we could remember We don't want to have our reactors explode, so we could say we vent emissions, vent, which usually for a bioreactor is not a problem. Okay. So now we're at the hold operation, inoculation. So there we only set how long it takes. We cannot set anything else. Nothing really happens. So we say that the inoculation takes 30 minutes based on our excessive experience in operating large-scale bioreactors. And we go to the next operation, and now we are at the ferment operation. Okay, so this is I would say the central operation, and we go first to the reaction as always. Also here we have a conversion of 100%, and then we go to the reaction and put in glucose. So we copy our equation, which is on the first page. We just copy glucose plus distiller soluble plus oxygen gives yeast plus carbon dioxide plus water. And now we adjust the mass coefficients. So it's 1 kilogram glucose, it's 0.1 kilogram distiller soluble, and it's 0.8 kilogram oxygen gives 0.6 kilogram yeast, 0.081 kilogram carbon dioxide, and 0.4 kilogram water. Check whether the masses are balanced. They are. Okay. Now we have set the conversion, and we want to here take care about the reaction heat. And what we have calculated is based on our oxygen consumption. You can directly calculate the heat of reaction. You have the oxygen, you just need to convert the oxygen. So what you do is you need to convert the masses of oxygen in moles and then multiply it with minus 460 kilojoule per mole, and that's it. And this you put then inside here to the reaction heat. And we set the reaction heat as kilojoule per kilogram. And if you would have calculated that, where's the value? It's minus 11,500 kilojoule per kilogram. What is important is minus 11,500 and not plus. Let's insert an error here. We put here a plus, an error which is always made by students. Usually you do these steps by yourself, and then I watch it because it helps if you have done this error yourself, and then you know how to solve the problem. So I introduced now here a typical student error. What is important is if you realize now, I entered it in kilocalories, or that you change now to calories per kilogram, be careful, this changes the numbers. So if you have typed in, if it was at calories per kilogram and you change now to kilojoule per kilogram, make sure that you look that the value is correct. Okay, now going back to operations conditions. Okay, this we have forgotten. Good that it puts an alarm. The reference compound for that per kilogram is, of course, our glucose. So this is the reaction enthalpy per kilogram glucose. Okay, now we go on, and we need to set before we finish. This is an aerobic process, so of course we need to have an aeration. And this aeration is now set here in this broth aeration setting. So we need to here assign the air supply stream. Let's go. It's the stream number. It's the port 11. So it's air that is already given in the composition, and we don't need to change anything else. This is the thing that we have aeration here. Okay, so now transfer out, we need to assign the stream for the transfer out, which is the stream number 6, fermentation product. Let's at least also here put the venting, but the remaining part, we're happy. Okay, so now we have done everything. And the cool thing is, what we can do now is we can perform the mass balance. So now the big moment comes, and we do the mass and energy balance, and we have an error. And now look at this error. The error, which is depicted here, is we look first at the red errors. Now, the operation requires heating, but chilled water has been selected. Please revisit operations data dialog to assign a proper heating agent. And in P1, the amount charged from stream water is 0. Oh, this means for the first operation, we have forgotten to charge some water. So let's start here and operation, charge 3. Oh, we have not given how much we want to charge. We want to charge 1,500 kilograms. So we do it again. Let's hope whether this error disappears. It doesn't, still there. So operation requires heating, but chilled water has been selected. Please revisit operations data dialog to assign a proper heating agent. And this is, you remember, I made an error by intention. I changed the reaction enthalpy, and you see now there is an error telling you that this operation requires heating. So it doesn't tell you that your reaction enthalpy is wrong because it's positive. It tells you you need to heat up the process. So to find this error, this means that you need to identify the problem, that it might be that the reaction heat is wrong. This is not so easy to come to that. This is why you're engineers and why you're not technicians and so on at the end. So if you have just and stuff which was not trained for that, you cannot expect that this stuff finds it, but it's expected from you, because later on you are the one who needs to set up these processes, and you don't have a professor. You can ask questions. So you need to train yourself in order how to be able to find this error. So you see, we first go operation, it's ferment P1. We have no other operations at present, and this operation requires heating, but chilled water has been selected. And we go to this ferment procedure in this ferment operation in this procedure P1. So let's go to ferment. And we go to reactions. And you see that the problem is something which, instead of produces heat, cools, and therefore this is the only thing which can produce heat at present is the reaction heat, and it should be minus. And if we now click OK, and we now redo the mass balance, now the error has disappeared. So you see, you really need to understand what is happening there in order to get rid of the errors. Okay, so now the mass balance has worked. Everything is fine. Mass and energy balance. We have also, of course, balanced the energy. And now let's see whether we're happy with the composition. So you could, of course, click on, right-click on also the fermenters and go to equipment contents doing P1. But we care about what is coming out. So we double-click on the stream here. And we look what is given here. And this should be the same as which is on our example. Otherwise, we had made an error. So we have distiller soluble. Of course, we have used the double amount which is required. So half of the distiller soluble is still there. The glucose has been completely consumed. This is good. It was our limiting substance. The amount of water has increased because we have produced water, and we have produced yeast. And you see that the yeast, so that's what we expected to have, and that's what we actually see. So you see that of this water, 92% is extracellular, 8% is intracellular. Of course, of the yeast, nothing is extracellular. Everything is intracellular. So this is fine. And we go now to the vent composition. So, and here it's also fine. It's 40 kilogram carbon dioxide roundabout. And we have also not produced nitrogen and oxygen. We have blown nitrogen through it, and we have consumed partially the oxygen we have used for aeration. It's a bioreactor. Okay. Now with this, we are happy. And now we also display the economic evaluation report. And this only works if you have saved it. So this is already a good time to save. And okay. And now we do the economic analysis. And now we go for the report, economic evaluation report. And then it said we should look at the utility costs. And you see this is our utility. So the costs will change sometimes a bit because it's adapted for the year. But the amount, you see, we need power, we need steam, we need chilled water. And at the end, we end up with annual costs of $7,600. And this is always adjusted depending on the price development. Okay, so this is what we have. The amounts are more or less the same as we have in our thing. Okay. We have now again set up a very, very simple process, which is kind of the same as before. We have a reactor. In this case, it was a bioreactor where I put everything in. The only change was that we had to classify distillers soluble from being similar to glucose, and we don't really know what is inside. And you see that the software is not doing a chemical stoichiometric balance internally, telling you where are my atoms. It doesn't care. You just you can write in everything you want, which makes, of course, the thing more flexible. However, this is then up to you to be sure that this is correct. Yeah. As one thing, it's a fermentation. It's now also we sparge in air. But at the end, nothing special. But now we want to get closer to reality. In reality, you will not use a bioreactor, which is really expensive for preparing your medium. Because the preparation of the medium, solving all the compounds and so on, mixing and so on, takes time. Weighing in the glucose and so on, it takes time. You don't do that in an expensive bioreactor. What you do is you prepare the medium in another device and then you pump it in. In your lab course, you do it in your shaking flasks and so on. But you only do it there because this is not a question of whether this shaking flask otherwise would be used for production of a valuable product. It's just there. But your bioreactor is expensive. And usually in a company, you have several production things running. And you want to use that for production. You see that at the end for debottlenecking. So therefore, you don't do that in the bioreactor to prepare the medium. You do that in another vessel. And then you pump the medium inside of the bioreactor. And of course, you would also sterilize it and so on using this method. Okay, so what we will do is we will add an upstream operation. And we just add a unit, which is just a vessel, where we then just prepare the medium and then we pump from this vessel the medium into the bioreactor. Of course, if you just have this reaction, it makes your process more expensive because you have another equipment. However, you cannot, of course, at the end produce more because when the bioreactor runs, you can already prepare the next medium. Why didn't we do that at, now you could ask, that was clear from the very beginning why, okay, I'm trying to tell it to you, but in reality, wouldn't it be wiser draw all the equipment which is required and then put in initialized streams and operations? And the clear response is no. Do it step by step. Start with your central unit, which is, for example, the bioreactor, and then make the process running. Look that there is no error inside. Then add another unit. You need to redraw some streams. You need to reinitialize some procedures. You will see that operations. You will see that in a second. However, the time you would save omitting this reinitialization steps is by far outweighed, especially for beginners, for the debugging. You have seen I have created now intentionally one error message. I had already two. Unintentional was that I forgot to assign the 1,500 kilograms with respect to the water. But if you have 20 operations and 20 units, which you initialize from the very beginning, and if you then do the mass balance, you will have thousands of errors. It takes ages to debug that. So I would strongly recommend develop your process unit by unit. Start with a central unit, in this case the bioreactor, and then add an upstream unit, and then redo the process, add a downstream unit, redo the process, look that the mass balance works, and so on. Okay, so we go now and add a blending tank. So let's go, unit procedure. And this is under storage blending, bulk, batch in a blending tank. So you see, this is also we feel the 500 submenu. There are a lot of units you can use. A blending tank. And we add this blending tank here. So this blending tank, which by the way, more or less looks like our reactor, what we have used. This blending tank we use now for the preparation of the medium. By the way, with the software, there are a couple of examples being delivered. So it's a wise idea, if you start with your process, look in the example processes which actually run to see how they have initialized procedures, operations, and so on. This helps. So the example processes are very valuable, not just this one. Okay, now we want to put this glucose distillate soluble and so on to this process. What you cannot do, unfortunately, is just move that. What we have to do is we delete them. So we delete the glucose stream, distillate soluble stream, and the water stream, and bring that a bit closer. So what we want to do is we want to bring in the glucose. We want to bring in distillate soluble, and we want to bring in the water. So can already edit that. Now we add first the streams. And now, of course, we need to transfer out from this blending storage tank to our bioreactor. So we have just connected an output of an import of the bioreactor. The air in we have kept unchanged, of course, because that's used for aeration. So now let's go and what is very important, so what I do first is usually I always first initialize streams in this case. So I want to have my label set. So I have again glucose here. I have, okay. And now what to do? Now we have drawn that, we have drawn the streams. We initialize the streams with the contents, glucose, distillate soluble. It's of course then again the distillate soluble, and the water. It's the water. So at present, what we have done is added the new unit, redrawn the streams, and initialized the streams. What to do next? So you remember we have removed streams from the operation of the fermentation operation. This worked. We knew that it works, this fermentation operation, but now it will not work anymore because we have procedures inside. We have discharge procedures which are no more of use. So the first thing to do is make this at least on the paper run again. So what I do now is before going to this blending tank, I go to the unit, to the fermentation operation where I have made changes and bring it back to a status that it works again, so that I don't need to care anymore about this. I need to care about then my new blending tank where I initialized everything. Okay, this means that we now go to the bioreactor, and in my fermentation tank, of course, I first need to change the operations which are there. So in this procedure, I had 3 charge operations, but these charge operations now will be performed on the level of the blending storage tank. So what I do is I need to remove them because they're of no more use. In contrast, what we need now is we now have a transfer in operation. So we will get we have a transfer out operation at the end, but at the beginning we transfer something from vessel A to vessel B, and this is a transfer operation. In this case, it's a transfer in operation. So we need to insert this transfer in operation, and of course it's the first operation. Therefore we put it like this. We put it in the top. So we have then changed it. We have a transfer in operation, heat operation, inoculation, ferment 1 and 2. So these operations didn't change with changing the streams, but we have a transfer in operation now. Okay. And of course, now we need to initialize this transfer in operation. So this is easy because the only thing we need to do there is we need to tell the operation what stream to use. And of course, it's the stream 104. So this stream here, and we have initialized now the transfer in operation with a stream 104. And if we manage to prepare the medium correctly here, it will be simply pumped into our fermenter, and that's it, and everything is fine. Okay, now let's go to the blending storage tank. So in this, we now need to initialize that it's actually making our medium, that we do it here. So of course what we need is at the beginning, what we do is we add the operations. So we add remove operations. Of course we need again 3 charge operations. 1, 2, 3. This didn't change. We just moved this charge operations from the bioreactor, from the fermenter now to this blending tank. Now we're a bit more precise. We say now we put everything in. Charging is throwing everything in. It makes sense to mix a bit. So we add an agitate operation. We mix. Yeah. And then we add a transfer out operation. So we have charged it, we have mixed it, and then if it's solved, we just pump it to the bioreactor. And this is, of course, a transfer out operation. So of course, again, we need to initialize the operations. So we right click, operation data, charge 1. And now we do the same as we did before. We charge, of course, the first one is charging with a glucose stream. So glucose, we charged 50 kilograms. And we go to the next operation. And this is the charge 2. This is distillers soluble. The same here. We set by user, it's 1 kilogram. The time is then 60 minutes. So we go back to the previous tab and set here also the time as 60 minutes. And then we charge our water. This time we charge 1,500 kilogram. We don't forget to put that. And we use the volumetric flow rate. The next operation we have is the agitate operation. And I have to check. This is just by setting the time to 60 minutes. And finally, we have a transfer out operation. And of course, the transfer out operation, we need to initialize what stream it uses. And this is the stream 104. And now, as we are so correct, we also venting. Okay. So now we have initialized the operation. We have first added the unit, drawn the unit, drawn the streams, initialized the streams, changed the unit operations in the fermentation procedure, eliminated the charge operations, which were no more necessary because they were now in our blending storage tank, added a transfer in operation and initialized this operation immediately by connecting the correct stream, which is the stream 104. Then we went to the blending tank, added the charge operation we previously had in this blending tank, initialized them with the correct stream and the mass, and the agitate was just the hour. And then we had the transfer out operation we initialized also with the correct stream. So that's it. And therefore, in principle, hopefully this works. And we have a lot of errors. Stream on output port in procedure 1. This is this is a lot of errors. So let's check what we have forgotten. We have used venting here. I know, because we were so precise. We used venting, but if you use venting, you should add a stream, otherwise it will complain. Now it's gone. Honestly, also, I was now a bit shocked having thousands of error messages, but be shocked, be cool, and then check what is happening. And you have seen that there are so many errors in this blending tank. This must have more or less a similar cause, and the cause was just that we did not add a vent here. If you don't do venting, you don't need this venting stream. Yeah, sometimes, as this is usually in processes. Honestly, I don't do the venting because I don't look at the pressures. If you have a vessel, this is implemented anyhow. This doesn't change anything with respect to cost calculations and so on. The only thing is if you would have a chemical which could be emitted to the air and you have to deal with that, then this makes a difference. But for our bioprocesses, usually this is not an issue. So therefore, I leave it usually without venting. In the example itself, the vent was not included, so there was no venting, with the exception of the bioreactor, where of course we need it because we blow in air. Okay, so now what we do is we double click on the fermentation product, and you see that there is no change, and this is good. We have exactly the same content here, and we have also here the same content. Now everything looks cool. So is everything fine? It looks like cool, everything is fine. However, to be honest, this was just luck that everything was cool because we have just initialized, but we didn't take care about any scheduling issues. And let's see where we find this scheduling. So we display on charts the operations Gantt chart. So again, you should also use these things as a manual. So we go to the chart, and now this is the operations Gantt chart. And what we see is we see when these operations are scheduled. So you see that this is the complete task. This is kind of the Gantt chart, the same as you see in scheduling software. Yeah. And you see we have here now our procedure P2. You see this is P2 is our blending tank. P1 is our bioreactor. The order is it starts with P2 and then with P1 because we have started there with P1. You could rename that also. I don't recommend you to rename everything, but sometimes it's better to put there another name that you see it. This is the vessel 101. This is our bioreactor fermenter 101. So we start with this. Within this procedure, everything is fine. So we have the charge operation 1, charge operation 2, charge operation 3, then we agitate, and then we do a transfer out. So this is fine. This order is correct. However, the transfer in operation of the second unit starts at the beginning. So in other words, by default, unit operations are set to start right from the beginning of the batch in parallel. And of course, that's not correct. So this operation, this transfer in operation, of course, should start at the same time as this transfer out operation here starts. And then also it should take the same amount of time as this transfer out operation. Only then it makes sense. So therefore, the complete process here should start there. And of course, there is a way to tell the software to do that. So we're at point 2.2.3, schedule operations. So what we need to do is we need now to tell the operations when to start. The cool thing is within a unit procedure, you have seen that automatically they're scheduled again according to the order they are put in. Therefore, the order matters. If you initialize and if you set up a new unit operation and a unit procedure, for example, a new fermentation procedure, and add 5 operations, make sure that the order is from the very beginning correct, because it automatically sets then the operations one after the other. This helps you, then you don't need to care about the scheduling there also. Yeah? Sometimes you need to change some things because some things might be parallel whatsoever, but in general, it's one after the other, and that's fine. So the transfer out operation of this blending storage tank here to this fermenter here, the transfer in operation, these must be linked. And indeed, the pumping out here dictates the pumping in here. And this is a master-slave relationship. Yeah? Of course, you could, when you do these operations here, you can at the same time already initialize and take care about scheduling. I would not recommend to do that. You have seen the complexity of the software is already high. So it's important always to reduce the level of complexity. That's also a learning intention here. Reduce the level of complexity. How can you reduce levels of complexity? By doing things step by step. So you should not do several things in parallel, because the likelihood that you introduce errors then increase exponentially. You should do things step by step. So this means I draw my unit, I initialize the streams, I add the operations, I initialize the operations, and then I do the scheduling. But because at each time I only have to think of one single topic, and this makes life way easier than if you have to think at the same time of hundreds of things, and you will forget something. And then you end up with 500 error codes and have no idea how to change it. Okay, so step by step. Now we take care about the scheduling. Now we are at 2.231. So it's a master-slave relationship, and the question is how to set this up. So if we go to our charts, Gantt chart, operation Gantt chart. So you see that here everything is correct. The transfer in operation was our problem. So we need to schedule the transfer in operation correctly. So this means we need to go to our fermenter, operation data, transfer in. And now you see that there are tabs, and there are tabs for the process time. And you remember the process time now should not come from this tab. It should depend on this transfer out operation, and the scheduling should depend on the transfer out operation. And you see, we can define the time by setting a master-slave relationship. So we can set by master-slave relationship. We go to setup. And now the slave operation is now our transfer in operation. That's okay. And the master procedure now is coming from another procedure. So we go now not to the fermentation procedure. We are at the procedure P2. So P2 is this blending storage tank. So master-slave relationship, another procedure, P2. And now it should match a single operation. And this operation, of course, also, now these are operations from P2. You see, these are charge, agitate, and this should match this transfer out operation. Okay. So you see, now we have set this master-slave relationship with respect to the duration, but this is not enough. We also need to set this master-slave relationship with respect to the scheduling. So the timing, scheduling means when does the operation start, and the operation conditions is how long does it take. But now we need to tell it also when does it start. And here you see the reference of this transfer in operation is relative to the beginning of the batch, which is of course not the thing we want. We want it to start relative to another operation in another procedure. So we go to this tab here. And the procedure again is our procedure. Hopefully we see it. Yeah, again, our procedure P2. And again, the operation is our transfer out operation. Click. And that's fine. And now we can schedule the dependency. So, and we start with the start of the reference operation. So you can define different dependencies here. But of course, as soon as the transfer out starts, the transfer in should also start. So we have now scheduled correctly the starting point. And we have now synchronized the times. You could also do it easier, by the way. You could also simply, if you have set this, then you can click sync with master, and then also the time is synchronized automatically. This makes things faster, but I wanted to describe it the long way, because I want you to make sure that you understand that master-slave relationships are always two things. One is the duration and one is the scheduling, and you need to take care about both. Now we have adjusted that. Okay. Now we do the mass balance. So if there would be an error now with our mass balance, it would be a miracle, because we didn't change anything about the substances and so on. So we should see, of course, now the same result here. If we click, you'll see there is no difference. But now if we go to charts, Gantt charts, operation Gantt charts, then you see things look different now. So you see now we have here our charge, we have our transfer out, and now you see that this transfer out and transfer in go exactly in parallel, and everything is fine. So what have we done today? We have added this fermentation reaction, and we have added an upstream reaction, and we have done a scheduling. That's it. We didn't do more. And honestly, that's it for today, because you need to digest this scheduling. So this is, you see that you need to really think in the process. That's very important. It's not just learning the software, clicking around, but even more importantly is learning to think how an engineer thinks, and this goes into the software. You see, industrial biotechnology is a combination of bioprocess engineering, business administration, and so on. This all gets inside, and the nice thing is this goes then inside of this piece of software where everything is condensed. And of course, this is something which is a bit complicated, because you see that our starting point for our fermentation was the calculation you did in the bioprocess exam. So you need that for doing for starting such a procedure. So it was not of no use to learn that for your bioprocess exam. So I know this is not so easy. However, the only way is do it yourself. I see your faces now at the monitor thinking of, but don't worry. At the end, using the software, as soon as you, let's say, are at a certain level of experience, is really fun, because then you know how to use a professional software. Digging into this software is a bit an effort, I know, but you come to the fun part. You have really acquired a new knowledge and capacity, and this is really cool. That's what I want. Yeah. So therefore, don't get frustrated. So this means, in other words, up to now, just setting up the basic process. We will proceed then with the downstream units next time, and we do then, of course, the debottlenecking and so on. But at that point, thank you very much for your attention. Don't get frustrated. You will come to the point where it's fun, and goodbye.